Hey guys, and welcome back to this class, Artificial Intelligence, Reinforcement Learning in Python. In this lecture, we are going to define the components of a reinforcement learning system. It might seem a little redundant at first because we already did this in the intro section, but you'll notice that as we progress further and further into the course, we're going to look at the same concepts each time, but make them more rigorous. We'll also add more components each time, so each time you'll learn about a few more terms, building on what you knew before. So in this lecture, we are going to again look at some concepts you already know a little bit about. There's the agent, that's the thing playing the game and the thing you want to program a reinforcement learning algorithm into. There's the environment, that's the thing the agent interacts with, it's the agent's world. There's the state, which is the specific configuration of the environment that the agent is sensing. Note that the state only involves what the agent can sense, not everything about the environment. For example, if I have a vacuum robot cleaning my house in Australia, then what's happening in someone else's house in India won't affect my vacuum robot state. Another example is if you have a self-driving car that has a 360-degree view of everything around it. If there's a truck in front of you, and there's a car in front of that truck, then that car is not part of your state because you can't see it. So your state would be the same, whether that car is in front of the truck that's in front of you or not. And finally, we have actions and rewards. Actions are the thing the agent can do that will affect its state. So in our tic-tac-toe game, that's placing a piece on the board. Performing an action always brings us to the next state, which also comes with a possible reward. One aspect of rewards is that a reward just tells you how good your action was, not whether it was a correct or incorrect action. It doesn't tell you whether it was the best or worst action, it's just a number. So if you're an agent, the rewards you've gotten over the course of your existence doesn't necessarily represent the possible rewards you could get in the future. You could be searching a bad part of the state space and hit a local maximum of 10 points, when the global maximum is 1,000 points. But you would never know that if you were the agent. We would know because we designed the game. That's again an instance of God mode knowledge. That's a lot like the life of a human being or an animal as well. You're born into a specific environment and you do your daily routine. You might find some things that make you happy, and you might consider that sort of a local maximum reward. But what if that person is living in some place without modern medicine or technology, and then you compare that to modern life and modern civilizations, you realize that the local maximum is nowhere near the global maximum. So everything is relative. Rewards are kind of meaningless numbers that only make sense relative to each other. In terms of reinforcement learning, more reward is always better than less reward. Now here's some funny notation. We know that being in a state, S of t, and taking action, A of t, will lead us to the reward R of t plus 1 and the state S of t plus 1. But when we drop the time indexes, we represent this for tuple as SAR as prime. We don't prime the R as you expect, which is odd, but it's standard notation. So the prime does not mean at time t plus 1. Now we are going to define some new terms. The first term we want to discuss is episode. An episode represents one run of the game. For example, we'll start a game of tic-tac-toe with an empty board. As soon as one player gets 3 of their pieces in a row, that's the end of that episode. As you can imagine, our reinforcement learning agent will learn across many episodes. So for example, after playing 1,000 or 10,000 or 100,000 episodes, we can possibly have trained an intelligent agent. How long it will take, of course, is a hyperparameter, and that depends on the game being played, the number of states, how random the game is, and so on. You should be used to hyperparameters if you've taken deep learning courses in the past. We call playing the game of tic-tac-toe an episodic task because you can play it again and again. This is different from a continuous task which never ends. So in a way, you only play a game that's a continuous task once. We will not be looking at continuous tasks in this course. When we talk about the end of an episode, there are certain states in the state space that tell you when the game is over. For tic-tac-toe, this is when one of the two players has 3 of their pieces in a row, or when the board is full. These states are called terminal states. So a terminal state is a state from which you can take no more actions. It means the episode is over. In terms of tic-tac-toe, that means either player 1 has won, player 2 has won, or it's a draw. Another famous problem in reinforcement learning and control systems is the problem of the inverted pendulum, as it's called in control systems, or cart pole, as it's called in reinforcement learning. They are the same problem. But if you search inverted pendulum on Google, you'll see research papers in the control systems field, and if you search cart pole on Google, you'll see research papers in the reinforcement learning field. At the beginning of an episode, the cart is stationary and the pole is perpendicular to the ground. But since this is an unstable system, the pole starts to fall down, and the job of the agent is to move the cart so that the pole does not fall. When the pole falls so far that it's impossible to get back up, any angle past a certain threshold is a terminal state. Note that because the angle in this system is a real number, this is a continuous state space, and hence there are an infinite number of states. We will not deal with continuous state spaces or state spaces of infinite size in this course. The idea of being able to learn from multiple episodes is kind of like the movie Groundhog Day. In this movie, the main character wakes up and lives through the same day every day. So it allows him to get better and better at making the most out of that day. That's like what happens to an agent in reinforcement learning. Even though you may lose a lot of episodes at first, you learn from them. Each episode is a fresh start. So eventually you get to the point where you are an expert because you've explored all the potential ways that an episode can proceed. So let's summarize everything we know about the components of a reinforcement learning system so far. We reviewed the agent, environment, states, actions, and rewards. And in this lecture, we learned about episodes and how an AI will learn across many episodes, and that the terminal state represents the end of an episode. In the next couple lectures, we'll look at some subtleties concerning reward assignment and how to do the actual learning.